Let's understand the number system in this video. Have you ever used pebbles to count things, like small toys or coins? Long ago, people did the same to count cattle and trade goods. And that started our story of numbers. First came natural numbers. The counting numbers 1, 2, 3, and so on. Archaeologists found old bones with notches, like the Lebombo and Ishango bones, that show people counted tens of thousands of years ago. These notches even hint that people noticed patterns, like prime numbers and doubling. In ancient India, trade and astronomy pushed people to make measuring and counting more exact. People named big powers of 10, like 10 to the 12, and even larger, which helped build the place value system. Next came a big idea from Indian thought, the idea of nothing, called Shunya or Shunyata. Brahmagupta, around 628 CE, turned that idea into the number 0 and wrote rules about it. He said if you subtract a number from itself, you get 0, like a minus a equals 0. He also gave rules. A plus 0 is a minus 0 is a, and a times 0 is 0. People then realized numbers could be negative too, to record debts and losses. Brahmagupta explained integers. Positive numbers are fortunes, and negatives are debts. So integers include minus 2, minus 1, 0, 1, 2, and more. He gave easy rules. A fortune plus a fortune stays a fortune, and a debt plus a debt is a bigger debt. If you multiply a debt by a fortune, you get a debt, and minus times minus gives a plus. Think of removing debts. Taking away 4 debts of minus 3 makes you plus 12. So minus 3 times minus 4 is plus 12. Now we meet rational numbers, written as P by Q, where P and Q are integers and Q is not 0. Examples are 1 by 2 or minus 5 by 7. And every integer is also a rational number, like 5 is 5 by 1. Rationals can look different but be equal. For example, minus 1 by 3 equals minus 2 by 6. In standard form, P and Q are coprime, which means they share no common factor except 1. We can add, subtract, multiply, and divide rationals using simple rules, and they stay rational unless we divide by 0. To check equality of two fractions, we use cross multiplication. A by B equals C by D if A times D equals B times C. On the number line, to plot P by Q, split one unit into Q equal parts and move P parts from 0. The absolute value is the distance from 0, always a non-negative number. And distance between A and B is absolute of A minus B. Rational numbers are dense, which means between any two rationals, there is another rational. For example, between 1 by 2 and 3 by 4, the average is 5 by 8. So 5 by 8 sits between them. But some quantities cannot be written as P by Q, and these are irrational numbers. Bodhain found that the diagonal of a unit square is the square root of 2, which cannot be written as a fraction. A short proof idea. Assume square root of 2 is P by Q in lowest terms. Then both P and Q become even, which is impossible. So contradiction. You can construct square root of 2 on the number line by making a right triangle with sides 1 and 1 and using Pythagoras. Another famous irrational is pi, which people approximated long ago, and Madhava found an infinite series for pi. He wrote pi equals 4 times the sum 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 and so on, needing infinitely many terms. Putting rationals and irrationals together gives the real numbers, the complete number line. Decimals tell us more. Rational decimals either terminate or repeat, while irrational decimals never end and never repeat. A decimal like 0.625 comes from 5 by 8 and ends because the denominator has only factors 2 or 5. But 1 by 3 gives 0.333, which repeats forever. And we write the dots to show repetition. You can convert repeating decimals to p by q by using clever multiplication and subtraction, as in turning 0.333 into 1 by 3. Some repeating blocks make cyclic numbers, like 1 by 7, which repeats 142857, and those digits rotate when multiplied. There is a curious fact that 0.999 equals 1 exactly, even though it looks different. Beyond the real line, mathematicians invented the imaginary unit I, which is the square root of -1. But that is for higher grades. So, what do we learn from this? Numbers began with counting and grew into a rich system that includes zero, negatives, fractions, irrationals, and more. Let us quickly remember. Natural numbers for counting, 0, and integers for debts and fortunes. Rationals as p by q, irrationals like square root of 2 and pi, and all together they form the real numbers. So today we learned how the number system grew, why 0 and negatives matter, and how rationals and irrationals are different. Keep exploring with simple examples on paper. Draw number lines and try the constructions for square roots. Learning numbers is a journey, and every little question makes you better at thinking. Keep your curiosity alive. And if you want to learn more, try the friendly lessons on EduRev at your own pace. Thank you for listening. And remember, math is a story you can touch and play with every day.